Hello everybody, my name is Nikolay Nikolov and this presentation is on TensorFlow, a system for large-scale machine learning. Today's date is July 1st, 2021, and this work is part of the TU Berlin seminar, Operating Complex IT Systems. My supervisor is Jonathan Will, and on this slide, as well as on the last one, you can find my contact information if you have any questions or feedback on the presentations. And we're going to start off with the content, just describing what this presentation will include. So the first part is the introduction. We're going to introduce the topic of large-scale machine learning. Then we're going to go into the background of distributed machine learning and TensorFlow. Then we're going to go into the core part of the presentation, the evaluation of TensorFlow's large-scale machine learning capabilities. We're going to also touch on the related work, other frameworks similar to TensorFlow, and we're going to end with a conclusion, just summarizing the whole presentation and the work involved. To start off with the introduction, it's important to ask the question, why large-scale machine learning? Why do we need it? How did we get to it? In order to do that, we need to understand a few phenomena that happened in the last couple of decades. We're going to start off with the digitalization. So we've seen this phenomenon happening in the last couple of decades. A lot of people now have access to personal computers, to smartphones, to smart devices such as smartwatches, smartbands, but also to IoT devices. We have smart homes, and so our lives are getting digitalized, and this, of course, leads to the collection of a lot more data that we can analyze and optimize on. This is often referred to big data. We're getting a lot of data that we previously couldn't analyze and collect, and so we're now able to improve our machine learning models on it and create new solutions. Also, we have easier access to computing resources. There are a lot of cloud solutions. Also, computing has become much more cheaper. Also, according to Moore's law, we're getting more performance very quickly. And so not only this, but we also have parallel computing advances. Things like HPC, high performance computing, has also made a lot of new solutions available, and we're now able to distribute it work on many devices. Also, these two things are related to declining costs, which means that more researchers and more people interested are getting involved in the field of machine learning, which makes possible that large-scale solutions are developed. And to end on the last one, we have AI frameworks. There are a lot of frameworks that engineers are now and researchers are now able to use, and these make the learning curve to get into machine learning and large-scale machine learning much smaller than it was before. Now, of course, there's an important question that we need to start with when we talk about large-scale machine learning. An important question is how to scale, right? So we have models that are used in smaller scale machine learning. How do we get from that to scalable machine learning solutions which can be used by more people? Well, it's important to say that there are also a couple of trends related to the phenomena as we talked about in the previous slide. And these are because of big data, the size of the training data has increased a lot. We're now collecting a lot more data. And because we have more data, we're also creating more complex machine learning models that often have millions or billions of parameters that need to be trained. So there is a need for a solution to scale both for the increased size of training data, but also for the more complex machine learning models. Mainly two ways to scale. The first one, of course, is vertical scaling. Vertical scaling is often referred to as making a single machine more powerful. This involves getting a single machine and making sure that it has enough resources for a more complex job. For example, it might have more RAM, it might have more powerful CPU, etc. And so this scales vertically. Now, vertical scaling is not a suitable solution for large-scale machine learning because single machines and their performance has not scaled as quickly as the collection of new data and the complication of machine learning models. Therefore, this is not a good solution. However, another solution is horizontal scaling. Horizontal scaling involves getting more but not so powerful machines that can work together, and the work can be distributed among them so that they can train different subsets of a model separately, and then they can communicate with each other and reach consensus. Now, in order to start diving into distributed machine learnings, it's important to keep in mind the scalability that we talked about right now. So we're gonna keep in mind the horizontal scaling, and we're gonna see how distributed machine learning uses that. Now let's start with the background. The background, the question that we want to answer is, what is distributed machine learning? Distributed machine learning builds on trends and advances in high-performance computing. It distributes work on machines, often referred to as workers or nodes, and it uses algorithm for consensus. For example, an exemplary architecture might look something like this. We have multiple workers, or often referred to as nodes, who work on a subset of the training data, and then they communicate and reach a consensus on the overall solution to the problem. Now, of course, this is related to a couple of challenges that we need to touch on. The system challenges, well, the first one that we can get to is resource management. Basically, the question that we need to ask here is how to allocate resources to many users and tasks. Often in distributed machine learning, we use clusters which are used by many users simultaneously and many tasks. So it's important to keep in mind resource management. Another thing that we need to think about is programming model. Are distributed models written differently? For example, if you write a model for only a single machine training, is it different than a model that can be distributed and trained on multiple devices simultaneously? Can we make a way to translate current models into distributed models automatically without having to manually rewrite models? Also, we need to think about communication. How can efficient input and output and data processing be achieved when we have distributed workers? Where is the training data? How do we distribute it in a secure and scalable manner? Fault tolerance is another important aspect. What happens if a node fails? How do we distribute it? How do we distribute its work to other nodes? Are there nodes who have a specific role, and what happens if they fail? Now, of course, consistency is also an important aspect. We need an algorithm that takes all of the small solutions of all of the workers and then reaches a consensus on the overall solution. So these are the system challenges that distributed machine learning faces. Now, a very famous distributed machine learning framework is TensorFlow, and we're going to show here a few of the basics of TensorFlow. So here is a quote on TensorFlow from the official TensorFlow.org website, and as you can see, it's not really clear what exactly it does and how it's built. It's an end-to-end open source system. It has an ecosystem of tools, and it's state-of-the-art ML and lets you research that. And it also lets developers build and deploy machine learning powered applications. But in order to understand it, we need to start from the beginning. We need to understand how it was built and what its predecessor was. Its predecessor, again developed by Google, was Disbelief. And Disbelief built on the parameter server architecture, which basically means that we have training data, we also have workers, which process a subset of the training data, and then we have the servers, which deal with the consensus among the workers and send the workers the newest parameters they can use for the next step. Disbelief was Python based, so Python was used to develop the scripts, and it was possible to compose predefined layers which could make a network similar to the one shown here or something experimental. Now, Disbelief. And so in order to understand why TensorFlow was developed, let's talk about the shortcomings of Disbelief, the predecessor. So one of the first one was that there was a barrier to defining experimental layers. So the layers in Disbelief were implemented in C++, and therefore a lot of the developers who only knew Python couldn't develop new experimental layers. Furthermore, Disbelief had an inflexible training architecture, and this made it impossible to do things such as recurrent neural networks, which require loops, or adversarial neural networks, which required two related networks, and reinforcement learning often was impossible because you needed a separate system, such as an emulator, where you compute the loss function. This belief was also inflexible in its training algorithms design, because things like offloading a computation onto the parameter server instead of the workers to reduce network traffic was not possible, and things like atomically updating a set of related parameters was also not possible, so it had an inflexible training algorithms design. Furthermore, it was non-platform agnostic system, which made it impossible to deploy on things like TPUs or more complex clusters, and also locally it was not so easy to work on a consumer workstation. Online services and mobile deployment integration was also not part of this belief. Now, TensorFlow improves on this belief by addressing these concerns, and it does so by making sure that all the primitive operators are building blocks of data flow graphs, which means that everything can be customized and everything can be done in Python. Furthermore, it had deferred execution. So after defining the static data flow graph, which is built up from primitive operators, TensorFlow could optimize the performance by analyzing the static graph, and this could lead to a higher hardware utilization. Furthermore, it offered abstraction for heterogeneous accelerators, because TensorFlow uses tensors as the primitive format for values, which means that all devices such as CPUs, GPUs, and TPUs understand this format, and so there is less need for device-specific implementation. Of course, there are some device-specific implementations which improve the performance on specific hardware, but the core principle is that tensors can be understood by all devices. Now, let's go into the evaluation, the core part of the presentation, and talk about the TensorFlow's capabilities for large-scale machine learning. The first one that we're going to go through is the support for processing units. TensorFlow supports different kinds of CPUs, the central processing units. However, CPUs have this bottleneck that this animation shows, which is that there is this von Neumann bottleneck. All operations need to end for the previous one to finish before they can start. So this means that we cannot do things in parallel. And while TensorFlow supports a wide variety of CPUs and also specialized third-party implementations, CPU usage is not really an important factor in large-scale machine learning. We rather need hardware such as a GPU, a graphics processing unit, which we can see in this animation can do multiple operations simultaneously because it has more ALUs, and so this is a fit for machine learning. Of course, TensorFlow uses NVIDIA's CUDA deep neural network implementation for GPU acceleration, and also there's a small drawback, which is that automated GPU acceleration is automated, and there is no control over memory usage. Other frameworks such as PyTorch allow for a more manual control over this, so GPU control is restricted on TensorFlow. Also, there is no native support for AMD, which means that acceleration on AMD is a cumbersome task and might not be possible in a quick and secure manner. Important aspect, and the last processing unit that we're going to talk about is a TPU, Tensor Processing Unit, which was initially developed by Google. It's a specialized machine learning processing unit, and it was developed by Google for TensorFlow workflows. It has a cheaper and faster performance, and we're gonna see an animation in a second which describes how it works. And Google and other vendors also provide cloud TPUs, which allows researchers and engineers to access that and have a quick performance based on the performance benefits of TPUs. Now, in order to see how TPUs work, we're going to see an animation here, which is showing that there are a lot of these matrix operation units, which can take a lot of the data simultaneously. And this is the first thing that we see on the left. For example, for an MNIST set, we get all of the data that we have seen, and then we're able to apply the model parameters to calculate the loss function or the prediction, and this is done quickly and without the need to access a shared memory, which is a bottleneck in GPUs. So the conclusion for the supportive processing units is that in terms of CPU and GPU, TF is comparable to other frameworks. However, its support for TPUs is what's making it more advantageous for large-scale machine learning workflows. The second evaluation that we're going to touch on is the one on mobile support. Mobile support is an important aspect of large-scale machine learning because a lot of the models are running on consumer devices and are related to consumer information. And it's important to know that one of the key features is low latency, which is achieved by doing the inference on the device rather than communicating with the backend machine learning server. Also, offline usage is made possible through the mobile support because there is no need to communicate with the backend server. And better privacy is also achieved by mobile support because there is no transfer of data to a backend server. Technologies, TensorFlow basically has an implementation for mobile support called TensorFlow Lite, and it supports Android, iOS, Linux embedded, and microcontrollers such as Raspberry Pi. How it does that is it optimizes a model by converting it from TensorFlow model to a TensorFlow Lite one, which is efficient. We're going to see how it does that through optimization steps. TensorFlow Lite does an optimization by either doing it automatically, which also reduces size and latency, but also impacts the model accuracy. And it also offers a couple of techniques for manual optimization through, for example, quantization, which is reducing the model's parameters precision by reducing the precision of the numbers representing these parameters. It also handles pruning, which is removing model parameters which have a minor impact on its prediction capabilities. And clustering is also possible, basically grouping weights of each layer into a predefined number of clusters, and then reducing the number of unique values by sharing the centroid values for the weights in each cluster. So basically, the conclusion of the mobile support is that TensorFlow provides a solution called TensorFlow Lite, which allows for low latency, offline usage, better privacy through model conversion and optimization, but it's important to know that this often results in less model prediction accuracy. And the third part of our evaluation is the deployment capabilities. The deployment capabilities are an important aspect, and they're the intersection between machine learning and DevOps, a new field called machine learning infrastructure. Without a solution provided by TensorFlow or PyTorch or any other framework, most often machine learning models are deployed inside a server implementation such as Flask, and a cold implementation might look like something like this. However, this offers no consistent APIs, no consistent payloads or model versioning, and things like mini batching or efficient use of hardware are also not supported in this. TensorFlow has a feature called TensorFlow Serving, which by saving a TensorFlow model, we're able to generate APIs and use Docker to deploy that. It handles remote models or local ones. It has mini batching so that hardware is efficiently used. It can also serve multiple models and versions simultaneously, and inference via REST and gRPC are possible. REST is mainly used for quicker and easier to understand communication, whereas gRPC is a very efficient but harder to implement communication protocol. ONNX support for non-TF models is enabled, which means that PyTorch and other frameworks could use TensorFlow serving to serve models. The conclusion for the deployment capability is that TensorFlow provides an automated solution for deployment, and it handles API generation, batching inference, Docker, model versioning, and all of the things listed here. Now, for related work, there are a couple of frameworks suited for large-scale machine learning apart from TensorFlow. These are the most popular of them, at least, are PyTorch, MXNet, CAF, and Apache Spark. They all have solutions for the different parts that we talked about. PyTorch is more popular towards researchers, whereas MXNet, for example, offers a very performant GPU performance. However, TensorFlow is more focused on large-scale production machine learning. The conclusion is, again, in terms of CPU and GPU support and also mobile, TensorFlow is comparable to other frameworks which also offer similar solutions. However, TPU support and integration with Google Cloud TPU is an important advantage, especially for large-scale machine learning. As we discussed, TPUs are very cheap and performant compared to other hardware, and deployment through TensorFlow serving can be scaled and maintained more easily than a manual setup, and also can be used for other frameworks. So this is the presentation. Thank you very much. And as we've discussed, here are a few links to get in contact with me, and I'd love to get your feedback and any questions you might have. Thank you very much.